This is the notes page for polynomial models, basically word problems. So we'll dive right in. The first one says a box with a square base and no top is to be made from a square piece of cardboard by cutting 4-inch squares from each corner and folding up the sides. We want to know this answer. We want to create a function that expresses the volume, and we want to know, once we have that function, if the box is to hold 100 inches cubed, how big a piece of cardboard is needed. So the first step is to always draw a picture, and this type of problem you want to become familiar with. It's like a two-step drawing. There's two things going on. You've got the two-dimensional piece of cardboard, which I'm pretending this is it right here, and then the three-dimensional box, which is formed from this cardboard. Okay, and so you want to be able to draw both pictures, so it's a good idea to do this once so you can have it right in front of you. But it says you've got a square piece of cardboard, this is paper, by cutting a 4-inch squares from each corner. So I'm not going to cut 4 inches, but I'll cut X inches from the corners like this. Okay, and so first thing we want to do is draw that picture. So we'll draw the cardboard and just mimic what we did. We cut out corners or squares from all 4 corners, and we're told that we cut out 4-inch squares. So this is 4 inches and that's 4 inches. And we don't know how big the cardboard is, so we're going to let the length of the cardboard be X. That's what we use variables for, to represent things we don't know yet. So that's a picture of the cardboard. Now, how do you make the box? Well, you make the box by folding up the edges. Okay, so fold up this edge and this edge. And notice that the base got smaller because we lost the edges, but you fold up the edges and now you have a box. Okay, so now let's draw that. So what I do is I usually draw the front and then diagonals, and these diagonals are all parallel, and then connect them. Okay, and that's my box. Okay, so now we have to label the box. Well, you have to visualize what happened was it was X inches long, but we lost 4 inches here and we lost 4 inches here. So how long is this now? What expression would represent the length of this box? Well, you can see we had X, we lost 4 here and 4 here. So now that's going to be X minus 8. It's square, so this comes from here, X minus 8 again. And I'll go ahead and write down 4 inches here, 4 inches here. So how high is it? If it's 4 inches and you fold it up, the height is 4 inches. Can't see, that's too bright. But this is the part gets folded up, and that's your height. So we now have a three-dimensional box drawn. And so now we can write a function that expresses the volume of the box, because we know that the formula for the volume of a box, a rectangular solid, is length times width times height. Okay, so v of x, function notation, the input is x, the length is x minus 8, and the width is x minus 8, So x minus 8 squared, and the height is 4. So there's your function. Now we can use that function to answer the question, the box is to hold 100 inches cubed, how big a piece of cardboard is needed? So we're looking for x, and the volume is 100 inches cubed. So we can put a 100 in for the volume and solve for x. Now, because there's only one x, you can use traditional algebra to solve for x. You can get rid of the first thing that happened to the x is minus 8, then it was squared, then it was multiplied by 4. So if we undo that in the opposite direction, we're going to divide by 4 first, and that gives us 25. And then if we take the square root, that's plus or minus 5 equals x minus 8. And you have to remember the plus or minus 5. It could work out. So that means that x minus 8 equals 5, or x minus 8 equals negative 5. If we add 8 to both sides, we get x is 13 inches. If we add 8 to both sides, x is 3 inches. Now there is a real world domain. If this is x, and you're taking out 4 inches here and 4 inches here, is there any way that x could be 3 inches? No. Okay, so the answer here, how big a piece is the cardboard? Well, it's a 13 inch by 13 inch piece of cardboard. Okay, so remember that type of problem. Practice drawing both pictures. All right, let's look at number 2. A large plywood box has the following dimensions. Its length is 9 feet greater than its height, and its width is 4 feet less than its height. And it's to have an open top. All right, it's breaking it down. We don't normally tell you this, but you get points on a test if you draw it. You want to be able to write a function for the volume of the box and then use that function that you create to answer this question. Okay, so we've got a large plywood box, and that's it, and you're given the dimension. So we'll draw this box. Again, I like to draw the front face first and then make the sides come out like that. So we have a length and a width and a height. And it says its length is 9 feet greater than its height, which we don't know, and the width is 4 feet less than its height. So the length and the width are given in terms of height, so that's a good idea that we're going to let x equal the height. So the height is x, and then it says that the length, we'll let this be the length, is 9 feet greater than the height, so that's x plus 9. And the width is 4 feet less than the height. That's not 4 minus x, that's x minus 4. So now we have labeled our 3 dimensions, and we know the formula is length times width times height. So our volume is length times width times height. This times this times this. So I'm going to put the x first because it looks prettier that way. Times x minus 4 times x plus 9. And it's feet, so we'll say x is in feet. Okay, so there's our function. Now it says find the dimensions of the box if its volume is 180 feet cubed. So here's some algebra that we're going to have to do. We're trying to find x again, and we're given the volume is 180. So we're going to have to put 180 in for the volume. And so what we have here, we haven't had one like this before. These are factored, but this is not equal to 0. So if you've got this in factored form and it equals 0, you're good to go. You can find your zeros. But this is factored and equal to 180. So bad news is we're going to have to multiply this out, set it equal to 0, and then refactor it if it factors. So got a little bit of algebra to work on here. It's always easier to deal with the binomials, multiply the binomials before you distribute the x. So that's what I'm going to do here. This is x squared plus 5x minus 36. Because your outer terms are 9x and your inner terms are negative 4x. So that's where that 5x comes from. And then That's x cubed plus 5x squared minus 36x if you distribute this x, and then if you move the 180 over, it's minus 180. So now we have it multiplied out, but it equals 0. All right, I think we can factor this by grouping, so let's try it. And it's our first grouping with a minus right here, so that's good to practice that. So the first 2, you can pull out an x squared, and that's going to leave you with x plus 5. Okay, and so here we want x plus 5. So that's how you decide whether you pull out a negative or a positive. If they're both negative, you want to pull out a negative. And let's see if 36 goes into 180. It does 5 times. That's good. So the GCF of negative 36 and negative 180 is negative 36. And you're left with x plus 5. So then it factors into x plus 5 times x squared minus 36. And then that factors, x squared minus 36 is a difference of 2 squares. That factors into x plus 6x minus 6. So now we've refactored it, and it equals 0. So now we can say that x equals negative 5, or x equals negative 6, or x equals 6 feet. And x is the height, so it can't be negative. So the height is 6 feet. Now what I like to do is go back to the picture to fill in the picture. So x is 6 feet, that's the height. X plus 9, that's 6 plus 9, that's 15 feet. And then 6 minus 4, that's 2 feet. Okay, so the dimensions of the box, it's a 6 foot by 15 foot by 2 foot box. So that's example 2. I like the algebra there. Okay, so example 3 is a new concept, and the box is already drawn for you, but I want to take you through this because you may not have the box drawn. It says the sketch below is a rectangular box. So if you were told that, you would draw your box. It has a depth of 10 inches, and it has an open top. So I'm going to just put a little arrow there that says there's nothing there. The box can hold a volume of 1,000 cubic inches, and that's it. So if you were doing this yourself, you would have a box, and you would have the height labeled, and you wouldn't have any knowledge about the width or the length. And you want to express the surface area of the box as a function of x. Okay, so you're given volume, but you want a surface area function. Okay, so here's a trick that you're going to use. What you want to do is you always want to label every important part of your picture. So when you start drawing this picture and you have 10 and nothing here, you have to say, well, let's pretend I know this. Let's let the length be x. And then I also don't know the width. I can't call it x because that would mean I'm assuming it's the same, so I have to choose a different variable, y. And this is the big deal. If you have a picture and you have 2 different variables, that's bad. Somehow you've got to get all your variables to be the same. So you have to get y written in terms of x or x written in terms of y. So that must mean that there's something in the problem you haven't used yet. Okay, so this is where this volume comes in. Why would they tell you the volume is 1,000 cubic inches? Well, they told you that so you could get rid of one of these variables. So we know the volume of a rectangular box is length times width times height. And we know the volume is 1,000, and the length is x, and the width is y, and the height is 10. So put them all together, you get 10xy equals 1,000. So see, now you have an equation and you can solve for y. So if we divide both sides by 10x, we get y equals 100 over x. So y is now in terms of x. So we don't have to think of y as y anymore. You can think of y as 100 over x. So that's the hurdle that you want to cross. You want to be able to draw a picture, label the picture, and then realize that if you have 2 different variables, there's got to be something in the problem that's going to let you write one of the variables in terms of the other. Okay, so now we're ready to find the surface area function. Call it S of x, and surface area means the area of all the faces, and there are 5 faces. Okay, so if you just look at this front, that's a rectangle. We know the formula for area of a rectangle is length times width, so this 10 is also this 10. So the front face has an area of 10x, and there's also a back face that's exactly the same size, so that's 10x. So this is the front and the back. Okay, let's do the left and the right. Well, the right has a length of 100 over x and a width, if you just think of it on its side, length times width, of 10x. So 10 times 100 over x, and there are 2 of those. Okay, so these 2 represent the left and the right face. Alright, so we've got front, back, left, right, one more, just the bottom, not the top because it's an open top. And the bottom is a rectangle, and it has a length of x and a width of 100 over x. So that's x times 100 over x. Okay, so if we simplify, and I'll just do this down here, you get s of x equals 10x plus 10x is 20x, and then 10 over 1 times 100 over x is 1,000 over x, and that's also 1,000 over x. So 1,000 over x plus 1,000 over x is 2,000 over x. And this x over 1, you can make anything a fraction. This x in the numerator cancels with that x in the denominator, and you're left with 100. So that's our function. So that is not quadratic. That's actually not even a polynomial. That's a rational function. So we don't have the algebra right now to solve that. You could use calculus to do it, and if you looked up the answer to this, you might see somebody take a derivative, but that's not this class, so don't do that. We'll just use desmos for this example. So I've already put it into desmos, and I just want to help you get better at using desmos. So you don't see the function because it's not showing up in this grid. So if we just kind of scroll out, you can see that it is looking like a rational function, and see x can't be 0, so there's a vertical asymptote at x equals 0. But anyway, we don't care about this bottom branch. We only care about quadrant 1 because x is positive. X is a length. Okay, so all you have to do is just kind of hover down here at the minimum, and if you push down, it'll find that minimum for you. And I'm getting a minimum of 10, 410. That's because I put the wrong thing in. Let's try adding 100 there. Now what's the minimum? I just had typo there. Okay, so you get what's the minimum is the ordered pair 10, 500, but I've been prepping you for this. Which one of these is the minimum? The minimum is actually 500. Okay, so this is actually a big concept here. You have to understand function notation. This 10 is x, this 500 is s of x. This 10 is x, the length. This 500 is the surface area. Okay, so the question is, what are the dimensions that'll produce a surface area? So 10, and the units are inches, 10 inches is one of the dimensions, because that's what x is. If you put 10 in here, you get 100 over 10, which is 10 inches. And then you know that's 10 inches as well. So the dimensions that are going to give you the minimum surface area are 10 inches by 10 inches, 10 inches. What is the minimum surface area? Well, that's the output. That's 500. And what are the units? Well, surface area is inches squared in this case. Okay. Question D, still on this question, if we wanted the surface area to be less than 750 square inches, what range of values would satisfy this condition? Well, let's go to desmos. Okay, so if we want the surface area to be less than 750, what I can do is put another equation in like that. So the surface area, you can't see there's an equal sign there. I don't know why it's not showing up. is equal to 750, and you can see that that happens here, and here is where the surface area equals 750. But the question is, we want it to be less than 750 square inches. So there's a range of x values. There's an interval from 3.441 inches to 29.059 inches. So that would be open parentheses, is less than, not less than or equal to 3.441 comma 29.059 inches. That's the range that's going to keep the surface area less than 750 inches. All right, next example. The area of the partition pen sketched below is 500 square feet. Okay, so again, I've drawn the picture for you, but the picture might have to be drawn by yourself. So the area of the partition pen is 500 square feet. We might say there are 5 partitions. So you would draw your 5 partitions. But this whole area is 500 square feet. Okay, so we don't know, and then we want to express the amount of fencing P as a function of the side X. Okay, so not sure why this has come out to be a V, but get caught off. We want the side to be X, so that tells me to label this X. All right, so we know the side is X, and then we don't know this, so we can't call this X. We have to call it something else, Y. So it's the same concept as before. First of all, not everything's labeled, so I would take time to label everything, every dimension. So this is X, 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 because they all have the same length. And then this is Y, feet long. Okay, so X is the side in feet, and Y we want to get in terms of X. So there must be something in the problem that's going to help us get rid of the Y. And sure enough, we're told that the area of the whole thing is 500 square feet. So the area of this whole thing is X times Y. So 500 equals XY is going to allow us to solve for Y. So Y is 500 over X. So now I can get rid of that Y and write 500 over X. And now we can write a function that expresses the amount of fencing. Well, the fencing is going to go here and 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 here, right? So we're just going to add that up. It's kind of like a perimeter, a special kind of perimeter. That's why we called it P, just FYI. So how many side x's do we have? 1, 2, 3, 4, 5, 6. So that's 6x plus 2 500 over x's. So that's 1,000 over x. And there's your function. And this time we don't need desmos because it says if the partition lengths are 13 feet, what will be the total amount of fencing needed? So these are partitions. Okay, so we're going to say this side length here is 13. So we're basically, this is an input-output question. So P of 13 is equal to 6 times 13 plus 1,000 over 13. And let's see what that gives us. So the perimeter would be 6 times 13 plus 1,000 divided by 13. And that's going to give us a perimeter of 154.92 feet. Okay, so example 5 is one that you've seen before. So I would stop the video and try this one. See if you can draw the pictures. There's going to be 2 pictures. See if you can remember why. See if you can label the picture and see if you can write a function of the volume in terms of x. And so I will give the answer after you have a chance to try it. Okay, so it says an open box is to be constructed by taking a piece of cardboard 20 centimeters by 40 centimeters and cutting squares of side x centimeters from each corner and folding up the sides. Find the dimensions of the box and write a function of the volume in terms of x so that you can find the dimensions of the box. Okay, so did you pick the cardboard and label it 40 by 20 and cut out X instead of 4? It's X. We don't know, so I put an X and 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 an X, X, X. Then I have to fold up the sides, so that's going to end up making the length of the box 40 minus 2X, and it's going to make the width of the box 20 minus 2X, and the height X. Okay, so then we can write a function, because we know function of the box is length times width times height. So I got X times 40 minus 2X times 20 minus 2X. Alright, now the next question, state the domain. So real world domain means there's going to be some restrictions on X. So obviously X can't be negative, the height can't be negative. Obviously the length can't be negative, it has to be greater than 0. And the width can't be negative. So if we solve all of these, we know X has to be greater than 0. Here, if I subtract 40, I get negative 2X is greater than negative 40, but then when I divide by negative 2, remember I have to switch the sign when I divide by a negative number. So X has to be less than 20. And then if I come over here and do the same thing, negative 2X is greater than negative 20. Divide by negative 2, I have to switch the sign. X has to be less than 10. So X has to be greater than 0, less than 20, but it also has to be less than 10. So this doesn't make sense if it has to be less than 10. So our domain is that X has to be greater than 0 but less than 10. So our domain is between parentheses 0 and 10. And then we'll leave it at that. We didn't get enough information to find the dimensions, but we've entered domain and write the function. Okay, now this next one I'll do with you. This one is a tough one to visualize, and this is what I mean. Now we could just give you a problem that you've never seen before, and you have to be clever. But don't panic. It says a piece of metal 50 inches wide is folded up X inches on both sides to form a feeding trough. So we want to write a function for the cross-sectional area in terms of X. Then find the height X. That will maximize the cross-sectional area. Okay, so this one is not easy because you may not know what a feeding trough is. You may not have an idea of what this is looking like. So basically what we have is we have a sheet of metal like this that's 50 inches wide. And we're not told how long it is. And you have to read the whole problem to figure out that we don't really need to know that. But maybe, honestly, the first time I did that, I might have been like, okay, that's why. And then it's not going to hurt anything. And then it's folded up to form a feeding trough. So what's happening is we're going to take a little bit from this side and a little bit from this side, and we're not told how much. So we're going to, it says X inches, right? And so you have to visualize if you fold it up, we don't need this piece or this piece. If you got a feeding trough and you fold up this side and this side, that's what we're talking about. And the cross-sectional area is just the front rectangle. That's what we're doing. So let me draw this picture. So what we have is we have this open kind of feeding trough like this. And I like to draw, and I find that when I'm drawing, sometimes it helps me understand the problem. So the cross-sectional area is just this front part right here. And then once I figure that out, and it took me a while. I mean, I'm doing this for you for the like the 100th time. Then I realized that that's why we didn't really need y. What we have here is we have 50 inches, but we are losing x on the left and x on the right. So this is 50 minus 2x. and this height is this x that got folded up. Okay, so this function, the function for the cross-sectional area is just this area, this rectangle. So that's x times 50 minus 2x. Okay, now back with me. I know that was hard, but now you got to come back with me. This is a big deal. How would you find the maximum area? How would you find x that gives you the maximum area? I love to take time to have people thinking about this, because this is the step that you have to, in this class, recognize. What is that? What type of function is that? Okay, that's quadratic. And we have spent so many lessons on the quadratic. You should know a quadratic backwards and forwards. Can you find a maximum if you have a quadratic? Yes, you can. Yeah, let's multiply it out. See if that jogs your memory. This would be 50x minus 2x squared, or negative 2x squared plus 50x. Do you remember how to find a maximum? Yeah, that's the vertex. Right, how do you find the x coordinate of the vertex? Negative b over 2a. So that would be negative 50 over 2 times negative 2. So 50 divided by 4 is 12.5 inches. So that's what x is. And now what would the maximum area be? We'll just plug that in. A of 12.5 equals negative 2 times 12.5 squared plus 50 times 12.5. So let's see what the maximum area is. We're finding the vertex, but it's the maximum in this context. Negative 2 times 12.5 squared plus 50 times 12.5. 312.5. What would be the units? Inches squared. So when these polynomial models, be on the lookout for, you've got to write a function. That's the hard part for students. But once you get a function, if it's quadratic, you can pretty much find anything that you need to find. You can find the maximum, you can find the minimum, you can find when it hits the ground. Quadratics are your friend. Okay. So number 7, I think you could probably do that one on your own. Try that one. Okay, so it says find the dimensions of the box described. The length of the box is 3 inches more than the height, and the width of the box is 5 inches more than the height. The volume of the box is 295 cubic inches. It says write the equation and then use desmos. So we can see if you did that. Alright, so first of all, the box looks like that. Since I don't know anything about the height, I'll let the height be x, and then the length be x plus 3, and then the width be x plus 5. So the function is v of x equals x times x plus 5 times x plus 3. And then you're supposed to plug 295 into the volume. And instead of like the first time we multiplied that out, set it equals 0, they said just use desmos. So I'll show you how to do that too. Okay, so I put the equation in. Sorry you can't see the equal sign, but v of x equals x times x plus 5 times x plus 3. And then v of x equals 295. So I put the left side in and the right side in, and then you can see where it intersects right there. Which one of these is x? The function is a v of x, so 4.322 is x. 295 is v of x, which we knew. So x is 4.322 inches. Okay, so now we can find the rest of the dimensions. This is 4.322 inches. This is 7.322 inches. And this is 9.322 inches. So the dimensions are right here. All right. Now we've got this last one where the function is given to us. A man owns a hot dog stand. He usually sells about 300 hot dogs per day at a price of $2 per hot dog. He notices that when he raises the price 10 cents, then he sells 3 fewer hot dogs. So that his revenue can be modeled by R of x equals 300 minus 3x times 2 plus 0.10x, where x is the number of price increases. So we could have gone through how to get this ourselves, but it takes a little work. X is the number of price increases. If he sells 300 hot dogs, but then every time he raises price he sells 3 fewer, then 300 minus 3 times the number of price increases is your quantity sold. And then if he sells the hot dogs at a price of 2, but he's going to raise it 10 cents, and x is the number of times he does that, then the price is going to be 2 plus 0.10 times the number of price increases. So that's your price, and that's what revenue is. Revenue is quantity times price. So we could have gotten that function ourselves, but I'm giving you that function. All you have to be able to do is find the price he should charge his hot dogs so that he maximizes his revenue. I know it's a video, but I'm having wait time. How would you do that? Look at the function. What kind of function is that? It's quadratic. So we can find the maximum if we can find the vertex. Unfortunately, it's in factored form, so we're going to have to multiply this out. So 300 times 2 is 600. 300 times 0.10x is 30x. Negative 3x times 2 is negative 6x, and negative 3x times 0.10 is negative 0.3x squared. So that gives me negative 0.3x squared plus 24x plus 600. Alright, so the x coordinate of the vertex is negative b over 2a. So negative 24 over 2 times negative 0.3 is going to give us parentheses, because I used the sideways division key, so I need parentheses. X is 40. What's that x stand for? Number of price increases. What do we want to find? The price. So that price comes from right there. So 2 plus 0.10 times 40 increases. That's going to give us $6. So he should charge $6. He's going to lose some customers, but he's going to end up making more money. Alright, there are so many other polynomial models we could do. There's lots in the lab manual, and the only way you get better at word problems is practicing. And I've gone through several concepts that hopefully you'll kind of take to heart. This last one, if you're given a function or you create a function and it's quadratic, try to remember it's quadratic. I know what I can do. I can find the vertex. I can find the when it hits the ground questions. So good luck with those word problems.